Hello and congratulations, you made it to the last chapter in Apes. Pat yourselves on the back. This chapter is going to deal with minerals and mining and the reason why you did the cookie lab and you mined in the cookie lab. So I'm going to ask, but before I ask, let's just take a look. So in this chapter we're going to look at mineral resources and their contributions to society. We're going to consider the different mining methods that are used. We'll also look at the social and environmental impacts of mining. We'll look at our reclamation efforts and mining policy, and then sustainable use of mineral sources. So those are the topics that we're going to be talking about, and this is a relatively short chapter, only 67 slides, so we should be able to get through this in no time. So this deals with the central case study, mining for cell phones. There is a little known metal called tantalum that is needed in every cell phone, a tiny amount. And this is what they are mining for. So I'm going to ask, and this is what I was going to ask you, to please make sure that you read the central case study that's found on pages 64 to the top of page 635. 634 to the top of page 635. Colton provides just one example of how we extract raw materials from beneath our planet's surface and turn them into products we use in our everyday lives. The lithosphere, which we've talked about before, is the region that includes the uppermost layers of rock near the Earth's surface. The rock cycle within that area creates the new rock and alters existing rock. The plate tectonics, as you remember making your books, builds mountains. They shape the geography of the oceans and the islands and the continents, and they also give rise to the earthquakes and volcanoes that we are familiar with. The Colton mining areas of the eastern Congo are situated along the western edge of Africa's Great Rift Valley system. This is a region that the African tectonic plate is still slowly moving and pulling itself apart. So we find in this area some of the world's largest lakes and immense valley floors, far below volcanoes such as Mount Kilimanjaro. And the geological processes that are in that area are fundamental in shaping the world around us. We find in these areas minerals that are non-renewable. So we need to be able to be aware of their finite and decreasing supplies so we know what is available for us, and also to be able to find alternative solutions for future development in technology. So just to go over a few terms, rock. You're probably saying, oh, this is ridiculous to define rock, but rock is the solid aggregation of minerals. And minerals are the naturally occurring solid chemical element or inorganic compound. And they typically have a crystal structure, a specific chemical composition, and they have distinct physical properties that make them up. And in order for us to survive, we depend on a wide array of mineral resources as raw materials for our products. And without these resources from beneath the ground, the civilizations that we know, the industrialized nations that we know, the developing nations that we know would not exist today. So when we take a look at this graphic, we can see all the elements that are made from minerals that we mine everywhere in the products that we use in our everyday lives. So if we're looking at glasses that we wear, the silica and the lithium in the glasses. We can also, in our vending machines, they're using iron and manganese and nickel and other things in the steel. The aluminum can, we touched briefly on this in the last chapter, is aluminum. In our money we have copper, nickel, and zinc. For our whiteboards it's called gypsum. that we use. As far as our makeups, we've got titanium and zinc and iron and copper and other chemicals and metals and minerals in our makeup. So our jewelry is either silver or gold. Sometimes it's also nickel as well. Your cell phone, as we've already discussed, has tantalum in it. The light bulb has tungsten. The paint that you have on your walls will have titanium and chromium and iron and candium. In your computers, we have nickel and candium for the batteries. And we also have lead, platinum and hafnium and gallium and indium and tantalum. I feel like that song, that chemistry song in the laptop. Your salt in your food. You have zinc and manganese in your batteries for your radios. Iron in the pen ink. Lead in solder that holds things together. And copper and zinc and brass in your belt buckles. So all of these are the different minerals that you have in the products that you use. So we obtain these minerals through a process of mining, and we've talked about mining. Mining is the broad sense, the extraction of any resource that is non-renewable. And we know we mine fossil fuels. We know that we mined even groundwater because that's what's in our aquifers. And we also mine minerals. So mining in relation to minerals is actually the systematic removal of the rock and the soil and other materials in order to extract the minerals of economic interest. So there has to be a separation that happens here. Because the minerals occur in very low concentrations, concentrated sources must be found before they can mine. So they're not just going to go into an area that they don't know if there's stuff in there. They're going to do a lot of testing and checking to see if there is concentrated sources that are present. If there's just trace amounts, then it's not even worth working in that area because they need to get larger amounts. We often don't notice how many mined resources we use. As you probably looked at that picture and thought, wow, I didn't realize. In 2013, the average American consumed more than 38,000 pounds of new minerals and fuels every year. And a child that is born in 2012 will, if we stick with the current rates that we are, use about 1.3 million kilograms or 2.9 million pounds during their lifetime. So they're going to use quite a bit. More than half of the annual mineral and fuel use is from coal, oil, and natural gas. As we know what is being mined, and mentioning that before. But the rest is from sand and gravel and stone. And these, as you know, are used in construction of buildings and paving and roads and etc. Metal use is small in comparison, but the average Americans will move more than 3 tons of aluminum. And as you remember in last chapter, there's enough aluminum in the landfills to supply the world. So we really go through a lot of aluminum. So here is this cute little baby. And in their lifetime, this baby will use about 978 pounds of copper, about 27,000 pounds of salt, about almost 12,000 pounds of clay, 521 pounds of zinc, 1.2 million pounds of stone, sand, and gravel. In their lifetime, they'll use almost 73,000 gallons of gas, 840 pounds of lead. Things that we're not mentioning here, about 53,000 pounds of the other metals and minerals, 6.63 million cubic feet of natural gas, over 43,000 pounds of cement, 27 pounds of iron ore, about 6,000 pounds of aluminum, over 445,000 pounds of coal, over 16,000 pounds of phosphate rock, and about 1.77 troy ounce of gold. So that's quite a bit if we're looking at the current rate of, in the year of 2013, that's what this child would be expected to use in their lifetime. So when we break this down, metal is an element that is lustrous, opaque, and malleable, and it can conduct heat and electricity. There are very few metals that are actually found in pure form, so they have to be synthesized. Ore is a mineral or a grouping of minerals from which we extract metals. And then economically, the ones that are most valuable are copper, iron, lead, gold, and aluminum. They are the most valuable ones. Tantalite ore is mined in a process into tantalum that we use in our electronic devices. And these are found mixed with columbite in our ore, and that's called coltan. So this is what coltan ore looks like, and this is what a capacitor would look like that contained this ore in order to run your cell phones and your devices. So most of the minerals must be processed after mining. They pull them out and then they have to put them through another regime in order to extract the minerals. After mining the ore, the rock is going to be crushed and the metals are going to be isolated by chemical and physical means. So there's going to be chemicals that are added, and then there's going to be physical things like further crushing and filtering. The material is processed to purify the metal, because we want pure metal. We don't want any residual rocks or stones or anything like that in there. What would you think if your gold came out and you had a little piece of gravel in it? So that has to be purified. And then this often requires the use of chemical solvents, and lots of chemical solvents. An alloy, you might have heard of alloys before, is actually a metal that's mixed and melted. It's also fused with another metal or non-metal substance, so it's a combination of things. So iron, the alloy of iron is carbon that you would get. And when you try to melt your minerals, this is referred to as smelting. And this is heating the ore beyond its melting point so that you're able to combine it with other metals or chemicals. So you all have class rings, or you got a class ring, and that lustrium and the yellow lustrium, these are examples of alloys that were put together by the process of smelting. So when we process minerals, this has environmental costs, of course, that we're going to consider. Most methods use a lot of water, and they're a lot of energy intensive, so that means that we're going to have a lot of emissions and a lot of byproducts and waste that we're going to have to deal with. And the chemical reactions alone are going to be creating different emissions. And heating these metals as high as they need is going to expend a lot of energy, and they're going to emit toxic substances and create air pollution. We're coming to the end of our time here, so we're going to end this at this point, and then we will start on the next slide. Have a good one.